Okay. So what we are going to do now, we are going to investigate one or two topologies to network monitoring agents, and based on that topology, we want to understand what is the messaging overhead for that topology and what is the cost of monitoring using that topology. Just to give you insight into why choosing appropriate topology and appropriate monitoring resolution is so important. So just imagine that you have 3 data centers. So you're using 2 public data center, 1 private data center, and you have distributed your 12 microservices across those data centers. And now your job is to write a monitoring algorithm that can collect information from all these microservices based on CPU, memory, response time, throughput, request, error rate, all those things. And based on what topology use, what is the messaging overhead, and what is the cost. We want to analyze that. And in exam, you could be asked similar question. Not the same, similar. For example, one of the approach which is very abstract, is trivial, is we write one centralized monitoring manager. We host it, say, in our private cloud because we want to avoid the leakage of monitoring data, and we get all the monitoring agents to send information to that centralized monitoring manager. So as I said in the previous slide, for every message you send out of your public data center to private data center, you pay money. However, if you send a message within data center, you don't spend any money. So in this case, all the messages sent by microservices 1 to 4 and 10 to 12 will cost you money, right? But all the messages sent by microservices 5 to 9 will be free. Okay. So based on this, we have to come up with a formula to know how much messages they will send on per observation interval. That could be every second, every minute, every hour. That could be anything. Okay. That's one topology. The other topology could be that each of the data center has a mid-level manager, and then there is a super manager in the private data center. So what's the advantage of this architecture as compared to this architecture? This is one way to implement your monitoring topology. This is other way to implement your monitoring topology. So what's the advantages or difference between this one and the other one? Cost cutting. What else? Yeah, well, cost, because then you can aggregate the local messages for this DC on this one. Then you can filter your messages in the local monitoring manager, and then you send information to centralize if and when needed. So you don't need to send every monitoring observation for every microservice on every observation point. So it's one other topology that can cut your monitoring cost and monitoring messages complexity by almost 1/4 in this case and 1/3 in that case, right? So based on what topology you're using, you will have different messaging overhead and different cost that you pay for sending messages from the public data center DC1 to private data center DC2. So what is to determine the messaging complexity? We have to come up with how many data centers I have. In each data center, how many microservices I have. In that microservices, each microservice is going to have one monitoring agent. And as I said before, if that microservice is in the same data center as the master monitoring manager, you're not charged for any messages, because either it is public or private. If you send message inside data center, you're not charged for that. You only charge for the messages that you send outside data center or from outside to inside. This is how the economics of public cloud works. If that data center where you have your monitoring manager is private, then you are not charged at all. Okay. So what you have to do is you have to first compute total number of messages sent by all microservices across all data center. From there, you subtract the messages from those microservices which is in that data center, which is determined by MPI. So MPI represents those microservices that is hosted in data center which has the centralized monitoring manager. So this equation will give you how much total monitoring messages is sent in one monitoring interval. That monitoring interval could be 1 second or 1.5 second as C advisor, or 1 minute, 1 hour. It's all configurable. It's based on your configuration, how often you want to monitor. So in the exam, what could happen is I can give this kind of architecture, give the monitoring interval, and can ask you to determine what would be the size of total data size that will send in one monitoring interval. So for example, the size of each monitoring message that we send from microservice to monitor manager is 2 megabytes. So in one monitoring interval, how many messages you will send? So you will send 4 messages from these 4 microservices, 5 from those microservices, and 3 for those. So 4 plus 5 plus 3. But because those 5 microservices are in the same data center, you have to subtract that. And size of this message is 2 MB, so you end up sending 14 megabytes of data on per observation. Okay, so this is important to understand which data center has the monitoring manager, and from those microservices, you are not going to be charged for the network traffic. So you will only charge for from this much traffic that is generated from DC1 and DC3, right? So for you to be able to solve this, you have to remember that equation and that relationship between in the exam if you really want to provide answers to this kind of questions. So this is for this topology. If we change to the other topology, right, where each data center has its own local monitoring manager. So in this case, what will happen is you only end up sending one message from here, one message from there. So you see, you cut your size from 14 MB to 4 MB. Just having just a split topology in which instead of sending everything to centralized manager, you have a mid-level manager that aggregates the monitoring information for that data center and then sends that message. So you end up just sending 2 messages because this one is for a local one. So you just end up with 4 MB. So based on what topology you use, you actually can have a different message overhead. So you cut from 7 messages to 2 messages, and also it also impacts how much data you actually have to transfer on per monitoring interval. And then next we will look into how this translates to actual cost of monitoring. So going to that example, so you are sending 14 MB of data per minute using their architecture. So in 1 year, you will be having this much gigabytes of monitoring data. 60 minutes, 24 hours, and 365 days. So if you multiply that for whole year, you end up with this much data, monitoring data, and based on current, say Amazon pricing policy, for each megabytes they charge you 0.003. So you end up paying $200 for monitoring bill. This is just for 12 microservices, right? So if you have thousands of microservices, you just have to multiply that with thousands. So you see, this is so it's not cheap. It's very expensive to even to monitor. Even for 12 microservices in 1 year, I will pay $200. If I have thousands of those just like that stocks in application, I will pay $20,000 in just for monitoring and collecting, debugging applications. So coming with appropriate monitoring strategy, keeping in mind how many messages I'm going to generate, keeping in mind how much it costs, keeping in mind based on what topology, how much messages I can save, will actually save you a lot of money in terms of your cloud deployment. And this is very important to understand in context of cloud economics. So cloud economics is not just about finding the cheapest VM or cheapest container. It's also about what kind of algorithm you use to monitor your application and what kind of topology you use to collect that information, process that information. So you have to keep those all things in your mind when you design your monitoring system, monitoring algorithms. So as I said, understanding this kind of topologies and messaging overhead is very important from exam point of view. I couldn't stress more than that. Right. Okay, so that was monitoring, and now we are moving to the last two orchestration operation, which is called as load balancing and auto scaling. So for that, just look at this animation first. So you're getting the request. So what is happening in this case? You get a request. So what's happening in this one? This is not monitoring, right? You are doing something else based on first request is sent to the web app server on this side, and the second request is sent on the other side. So what's happening here? what is being done by the load balancer? It's balancing the load, right? Then the question is, how do we balance this load? So what is the one key thing that load balancer needs to be able to balance this load correctly? Again, the monitoring information, right? What is the current load of this web server, this app server, this web server, and from that statistics, we will be able to determine which app server, web server is good for this request. So again, monitoring is so important because it feeds into how do you balance your workload across your app server, web server, or this could be even microservices as well, and based on that. And of course, there are so many literatures, so many algorithms available in literature for load balancing across monolithic application based on VMs. However, most of them don't apply to microservices load balancing. I'll explain why it is that. Because in the old days, when they used to do load balancing VM application, we have the whole application logic inside the application container, application VMs. It was a piece of code that has all the dependencies inside the one instance. But in microservices, we said we distribute the logic across multiple microservices. So then the old way of balancing load is not going to work. So that's why now we have two types of load balancing. One is layer 4 and one is layer 7. So layer 4 is at the transport layer, where you just look, where you think that all the application logic you need to process the request is available in the app server. But in layer 7, it is customized for microservices, where you know what kind of request you are getting, and those requests can be served by which microservice. So it's more at the layer 7. Of course, to do at the layer 7, we need something more, so we will discuss that in detail. So to summarize, so load balancing is other key challenge in cloud computing. Why would be that? If my application is not load balanced, what could go wrong? Even if I had done the benchmarking, image selection, I'm doing good monitoring, if it's not load balanced, what could go wrong with my application? I'm just not using my hardware and software in an optimal way. So my system is not optimized. For example, if we go back to this picture, if this is not load balanced, then all the requests comes to say the servers on this side. So what will happen is that this will get overloaded, and your cloud auto scaling engine will keep scaling this again and again, while the other side is underutilized. So this is, if your infrastructure is not load balanced, you will end up paying more to the cloud provider. At the same time, you will have not very good quality of service in terms of response time and throughput to the users. So load balancing is also one of the critical things to consider when you deploy application on the public cloud and the hybrid cloud, because that will determine how much hosting cost you pay to the cloud provider. That will also determine how satisfied are your users who are using your applications. So main goal of this load balancing is to keep your system in a stable state. So you keep balancing your load across your app servers and web servers in such a way that your system, similar to this animation, is always in the balanced state. It's not falling down. Okay. And again, as I said before, the actual load balancing algorithm needs a lot of information for monitoring system. That could be CPU utilization, memory utilization, IO utilization, response time, throughput. All those information are required for the load balancer to be able to make those decisions, which is the best instance to put the request across the servers. So just to demonstrate an example, so if we had 3 hosts, one host had Tomcat, MySQL, other had MySQL, other had Tomcat, MySQL, and how load balancing works. For example, if you end up with this scenario, so if you look at the host 1, and if we are not load balanced, what will happen is you will reach the saturation point for that server, and after that, that server will start dropping the request. So you're losing your clients, and then the clients will stop coming to your server, and your saturation will go down. And then your monitoring system will say that everything is fine because now it's non-saturated, right? So that's why being first able to do a proper load balancing is important. At the same time, doing a proper monitoring to know why my utilization has come down. It is because my system is optimized, or it's because request has stopped coming to my server. That's why doing load balancing is so important. Because if your system is not load balanced, after the saturation point, that server will stop dropping the request, and then automatically the request will be just not served to the user. User will stop coming, and then it will come down, and the system become unstable. So in the exam, you could be asked what's the relationship between monitoring and load balancing, and how they're required. What is the importance in terms of managing your cloud application deployment at runtime? How monitoring and load balancing are related to each other. So although cloud computing helps you scale on demand, but to be able to use that scalability feature in a way that is useful and optimized, you need a proper load balancer. And the main goal of load balancer is to distribute your workload across multiple servers to meet your application workload while meeting the user's response time constraint, user throughput constraint. At the same time, ensuring that the CPU and the memory and network I/O on the servers are not saturated. So you see the load balancer has two-dimensional function. One for the user, that you want to make sure the response time throughput are appropriate, and for the servers, that CPU, memory, and the network is not saturated. So that load balancer needs to do some very complicated decision in order to serve both the hardware as well as the users. So it has to balance between those competing decisions. So what can load balancer do if it finds that all my servers are saturated? What could be the next step it could do to fix the problem? It needs to do that automatically. So it just found out that all my web and app servers are not saturated. Now, doesn't matter how sophisticated load balancing technique I use, I am not going to fix the problem. The clients will not get the request solved. What could be a solution for that? If everything is saturated, what do you do in cloud? You just ask to add a new server. So that's where you come use auto scaling. So when after doing all those complicated load balancing across these servers, found that each of them is now saturated. Doesn't matter how sophisticated technique I use here, I cannot make anything work. So the next step for it is to go to the auto scaling service or auto scaling algorithm of that cloud and add one more server. So that's also part of runtime reconfiguration. So this is how the monitoring, load balancing, and auto scaling works together. This is like a closed loop. Right, so I was saying there are two kinds of load balancing possible in cloud computing. One is layer 4. So this was the tradition before microservices came into picture. This was more for monolithic application where whole application logic is inside one virtual machine. For that you can layer 4 load balancing, but layer 4 load balancing doesn't work for microservices, because microservices will distribute the application logic across multiple decomposed smaller units. So pretty much we need to do load balance based on what feature is offered by that microservice. So layer 7 load balancing is not very different from API gateways that we studied in last lecture. Remember the API gateway that connects to multiple microservices based on what feature they provide. So mostly API gateways are implemented based on layer 7 load balancers, because that's what they are doing. They are routing the request to different microservices based on what API feature, what content they are serving. So one of the way to implement the API gateway that we studied in the last lecture is through a layer 7 load balancer in context of microservice-based architectures. Okay. So going back to the old days when they had this, when they didn't have the microservices, they used to balance workload across different virtual machine instances without considering what application logic is inside those instances, because each instance had the same application logic, so it doesn't really matter. And in those days, you have many heuristics they use. For example, they use round robin. So round robin, the name implies you give each to one of the instances, and then you come back to the first instance when each instance had the same number of requests. Then they had based on least loaded, so they just used to monitor the CPU, memory, and network for each of the instances, and the next request is given to those instances that has the least load in terms of those parameters. Then based on least number of connections, least traffic, so there are many heuristics that we use those days. However, these are not so applicable in context of microservices. So for microservices, you have to keep this into account, plus you have to add some new features on to also understand what part of application logic is offered by that microservice, and then combine these heuristics with those features to do new load balancing. So for example, now if someone wants you to write a load balancing algorithm for public cloud, even that's not easy anymore, because you have to understand whether I have to balance on layer 4 or layer 7. Based on either layer 4 or layer 7, you will use different algorithms. So even that gets complicated as well. Just simple load balancing across virtual machines or microservices. So you need to understand what is the composition of my application architecture. It is based on microservices, whether those microservices are actually doing the decomposition of the application logic. If they are just containerizing the old code, then you don't need layer 7, just you can use layer 4. But if those microservices are actually decomposing the application logic, then you have to go into layer 7 load balancing and employ that technique to balance the load. For example, if you go to Amazon Web Services, they offer you two kind of load balancer. One is layer 4, which is the old one. It's called EC2 load balancer, and then there's a new one called layer 7 load balancer. But then again, which one you use depends on how you have programmed your microservices and what kind of logic you have put inside your microservice. It depends on that. So as I said, it works at the network transport layer. So it actually just gets a request and then just balances it across the instances. It doesn't care about what is actual request contains. For example, it is asking for which kind of content. For example, the request could be just for static images. Some requests could be to buy some books, for example. Some requests could be get a video. So one application can have different application logic, right? For example, if you're running an online book application, some request could be just want to see the pictures of the book. Some request could be I want to buy, so I want to put my credit card details. Some request could be that I want to give my address to the warehouse or distributor. So, but this kind of load balancer doesn't look into that, because all those three steps that are described is implemented inside the one instance. So it doesn't look into those specific of what is actually being requested. But if I replace the same instance with decomposed microservices, and I want to do load balancing based on what feature offered by the microservice, then I actually need to parse the HTTP or HTTPS header and see what kind of content or request that user is making, and based on that, I redirect that request to that particular microservice. So this is the difference between the layer 4 and layer 7 load balancing. Layer 4 doesn't care about the message itself, it just balances blindly. But layer 7 load balancing actually parses the HTTP header and trying to find out which microservice is actually going to serve this request the best based on what content they are offering. For example, you just want to view a page, or you want to buy a book, or you want to put in the address. Based on that, it can automatically map the user request to those microservices. So this is how you can take advantage of the decomposition of microservices and bring it all the way back to the load balancer. So this layer 7 load balancing is also called as URL-based routing policy. So what do you mean by URL-based routing policy? Is like when you configure load balancer, you can say that if the user is asking to view a book, put to X microservice. If user is asking to purchase a book, put to Y microservice. If user is asking to pay for the book, put in a Z microservice. So you can do this content-based or URL-based routing. Okay, you can parse those URL from the HTTP header itself. So that basically means the layer 7 load balancer needs more intelligence to be dealing with those requests as compared to layer 4. So layer 4 load balancer pretty much like a dumb code, because it doesn't care about what's inside the request. So layer 7 doesn't work like that. It actually has to go and parse each request and see what kind of content the URL it's trying to address, and based on that, it does load balancing across different instances of microservices. So obviously, as I said, layer 7 load balancers are only good for nicely decomposed microservice-based application. Layer 7-based load balancing doesn't make sense in context of virtual machine-based monolithic application, because in those applications, all application logic is contained inside a VM. So either use layer 7, layer 4 is not going to make any difference. So layer 7 is only used for those applications that is decomposed in a proper way using microservices, and then you can always differentiate between the different features offered by different microservices. So this is some design issue you have to keep in mind when deciding either I go for layer 7 or layer 4 load balancing. So this is one of the snapshot from Amazon Web Services. When you go to deploy your application here, they will give you option of either you want to use classic load balancer, application level load balancer, and based on that, it will do things differently. Now we are going to the last operation of the orchestration, which is called auto scaling. So say we had this different hosts running, and each of them had the monitoring agent. I am balancing all the workload, but what happens is that everything is saturated. Doesn't matter how I am going to balance my load on layer 7, layer 4. It's not going to improve the utilization of my servers. Then what do we do next? This is part of the runtime reconfiguration. That brings us down to the last operation of orchestration, which is called auto scaling. So scaling is just not because everything gets saturated. What also happens is things fail, and things failing is very normal in cloud data centers. Like your container can fail, your VM can fail, and once that failure detected by the load balancer and the VMs or by the monitoring engine, you have to do certain actions. So to counter that challenge, you need to have a proper auto scaling algorithm. So of course, this cloud providers gives you some basic technique that you can configure rules that, okay, if my CPU utilization for my instances goes more than 80%, add a new instance, right? But that's very trivial. Or if something fails, add a new instance. But this is not actually, for example, those kind of scaling will not take into account the actual needs of the application. For example, you are just scaling the DB layer that you may not need to scale. You might just need to scale the web layer, but that only you can know by actually monitoring and finding the problem yourself. You just can't rely on the cloud provider to scale your system. For example, if I have a container engine in which I'm running one web container, one DB container, and one say app container, and my utilization is getting high because of DB container. But if I'm just scaling that VM again and again, I'm also scaling the app and the web layer that I don't need to, right? So this can only be not done if you actually not host all this component on the same host, first thing, and second, you actually need to know through monitoring, debugging, which component needs real scaling or which doesn't need the scaling. So again, just using the basic auto scaling provided by the cloud provider is not sufficient to serve your application. You need to write your own algorithm and then use the monitoring debugging techniques to know which components really need scaling, not all of them together. So auto scaling is a method used in cloud computing where the amount of computational resources given to VMs and containers are automatically changed based on CPU, memory, network response time, and throughput. And auto scaling is very essential for you to enable elasticity, how to automatically adapt to failures, to saturation, underutilization, overutilization, but also to the fault tolerance. So auto scaling means you add more cloud server, but you also sometimes need descaling as well, right? So for example, you end up adding scaling from 5 to 10, and now your utilization goes down to 20%, right? Then your system orchestrator also needs some way to bring it from 10 to 7. For example, maybe on 7 years utilization is 70%, right? So auto scaling is just not one-way exercise in cloud computing. You also need to sometimes descale based on your application workload. So that, again, all those decisions are going to be part of your auto scaling logic. Then only you can take advantage of the actual elasticity offered by the cloud providers. For example, if you find that one of the hosts has getting saturated at 80%, the auto scaling service can add one more VM, and then you can bring the overall utilization to less than 50%, 60%. So as I said, if you use the Amazon Autoscaler on Amazon Web Services, you can configure the rules. For example, it says that add one extra instances when the CPU utilization of existing instance between 30 to 50%. You can add 2 instances when the utilization of my existing instances goes between 50 to 70, or add 4 instances when my utilization between 70 or higher. So these are more kind of static rules you can supply to Amazon Orchestrator, and they can do the auto scaling for yourself. But I said these auto scaling technique doesn't take into account your actual application architecture. It's going to scale everything that's running inside the instance. But perhaps the reason could be you don't need to scale everything, you just need to scale one of the components. That's why you need your own auto scaling technique to really be able to have optimized auto scaling over public cloud provider. So the key message here is to be able to do proper cloud application deployment engineering. You need to understand the challenges of each of those steps, being able to use the appropriate framework for each of those steps or algorithm, and then have to make sure that each of those work together in a cycle. So this is the whole life cycle of cloud application deployment and management. And as I said, each of them are NP hard on its own sense, so you need to find appropriate algorithm that solve that NP hard problem in some reasonable time, and they work together. That's why managing a production scale cloud architecture is very, very challenging. Obviously, not all these 4 steps given to one engineer will work as a part of thousands of engineers, but you have to work across different teams. Some does virtualization, some does in networking, some do monitoring, some do auto scaling, but everything together has to make sense. But before you can start working on that kind of large scale data center environment, you need to understand what are those orchestration operation algorithms I need to be aware about to be able to program, deploy, and manage the application on cloud infrastructure.